Hello, welcome back. Today we're going to investigate most people's favorite topic, at least one of my favorite topics, and that is magnets and magnetic fields. And so what I'd like to do here in the beginning is kind of talk a little bit about magnetic fields, but mostly I want to film it in slow motion. So we've all seen the iron filings that you can sprinkle on top of magnetic fields, and you can see the beautiful patterns, right? And what I would like to do is I'd like to show you that first, but then I would like to suspend a magnet in three-dimensional space with a string, and then I'd like to literally get my hands and throw the iron filings in the air so they kind of like float up and kind of on top of the magnet and crisscross over. And then I would like to film that in slow motion. I would like to see what do the iron filings do when they get in proximity of the magnetic field. How exactly do they align themselves, and kind of zoom in on that and film it all in slow motion. I think it would be really cool, and that's what we're going to try to do today.
To me, this sums up why magnets are so cool. When you put two of them on top of each other and flip them to the right polarity, you feel a repulsive force that's very springy in nature, yet totally invisible. Now, classical theories of physics, and that just means physics theories that don't involve quantum mechanics, describe this effect by an invisible field that surrounds magnetic materials. And one of the easiest ways to see this is by taking the magnet and sprinkling a magnetized material on top, like iron filings, which are able to be influenced by the magnetic field. So what you see when you sprinkle these iron filings on top of a bar magnet is an invisible field of lines that surround these materials. You can see one end of the bar magnet has a much more densely clustered field lines entering in one side of the bar magnet, and as it extends around the bar magnet, entering into the other side. The strongest part of the magnets are near the ends where the field lines are more concentrated. Now, I'll be filming the magnetic field lines forming in slow motion in just a second, but before we do that, here is a oil-filled flat panel with iron filings inside. And when you suspend it directly above a bar magnet, you can see the magnetic field influence the iron filings immediately inside of the fluid. And the formation of the magnetic field, as you see, is very, very pronounced. And although it's only in a flat plane, you can imagine extending in 3 dimensions all the way around the magnet itself. And as we slide the filings across the top, it's really cool to see the influence.
Here is iron filings. We're going to do a lot with iron filings, but here is just a fluid-filled box here full of iron filings. So with no magnet inside, you can see what's going on here. Let's drop this thing in here and see what happens. We'll drop it in there and look at what happens there. You can see the magnetic field immediately appear. In fact, it's a little more impressive if I close it off here, and you can see it's sort of attracting inside of there now. And if I give it a nice little shake, and I'll try to get the angle with a couple of different cameras. So there's sort of a side view there. Let me kind of let it go so you can sort of see that. And then we'll do it with sort of the top view there. And so you can see that the field is exiting and coming around. You can see the curved nature of the field as it comes and sort of enters into the bottom.
And of course, the magnetic field around a circular magnet would look a little bit different. Now let's try to film the influence of this magnetic field in slow motion. Now here's our first attempt at slow motion. I've suspended a bar magnet and literally grabbed 2 handfuls of iron filings and threw them at the bar magnet. And if you look closely near the ends and near the center, you can see the influence. Here's the same shot zoomed into the center, and you can see the iron filings forming little arcs as they pass over the top. The next thing I did was to try to grab even more and throw a larger volume so you can see the clumpy nature of it, and you can actually see the influence even better when I threw more of the iron filings, and you can see the magnet swinging back and forth on the string. As a point of reference, I grabbed some non-magnetic glitter that I threw in the same fashion, and you can see that when you throw glitter at this magnet, there's absolutely no influence from the magnetic field, or very minimal influence. As the glitter flies across the surface, you can see it following more or less a straight line or a parabolic trajectory under gravity, not really being attracted to either side of the magnet. And I want you to remember this picture whenever you compare it to how the magnet influences iron filings, which are magnetizable. This is one of my best throws, I think. I reduced the amount of iron filings in my fingers and I tried to sprinkle it in a more dispersive way. In other words, tried not to make it so clumpy. And when these iron filings approach the magnet, I think you can see the influence a little bit more pronounced. Also, this is at a higher frame rate, so things look a little slower. As we get close to the magnet, you can clearly see the arcing nature of the magnetic field, and you can almost see some of these iron filings orbiting and kind of being flung around the end of the bar magnet where the magnetic field is the strongest. Now, every once in a while you have a pretty good idea, and I think this is one of them. You can't tell too much here, but I actually twisted the magnet and let it rotate in 3D space. And so I caught an angle shot where the iron filings are approaching sort of obliquely from the side. And I think what's awesome about this is the filings kind of orbit around. They're kind of captured by the magnetic force and kind of get slung around and thrown around as they're attracted to the magnet. Now this was cool. Here's a circular magnet where I throw the iron filings, and if you watch closely, as you see the iron filings go toward the center of the open area in the middle there, they get rapidly attracted from the inside, and it almost looks like some kind of vortex or black hole as they rapidly go to the center and then are attracted to the inside of that annular ring. I think that's worth a close-up look at how the magnetic field influences the iron filings as they approach the center, rapidly grab them and pull them out. Here's my close-up lens showing the very end of the bar magnet where the field is strongest, and you can really see those iron filings being stretched into these sort of long, thin tendrils that get attracted and get clumped on the end. Here's a similar close-up shot with even more iron filings, so it clumps even more, and you can really see the influence as it stretches out these iron filings and attracts them violently to the end there. Now here's a little fun shot where I wave the magnet back and forth just above a line of iron filings. And as they come under the influence of the magnetic field, they begin to kind of clump together and kind of like leap off of the page, resembling kind of like little spaceships launching into the sky or something like that. And they get drawn in these long tendrils of these spiky formations before detaching and launching themselves up to the magnet. I think in slow motion, it really adds a lot to the magic of what's really happening here.
So now that we've looked in slow motion how magnetic fields really behave and how they influence matter that's able to be magnetized around it in the magnetic field, let's take a few minutes to dive a little bit deeper into the concept of a magnetic field. Specifically, how do magnets attract and repel each other? Here is a bar magnet, right? Here is another bar magnet. All bar magnets have some north and south pole. I'm going to draw this one north-south. I'm going to draw this one north-south. Now, how are these things going to behave? Same poles are going to repel each other. We know that to be the case. Let's draw the magnetic field, not the whole field. We'll just draw kind of a little portion of it. It comes out of the north, goes into the south. So this way, this way, this way. It goes out of the north, into the south, right? This one is going to go this way, and it's going to connect again to its south pole, out of the north, like this, and in to the south. Right? Now what's going to happen as we push these things closer together? Notice that the direction of these arrows are kind of pointed at odds with each other, but the closer I get them, what's going to happen is they're going to be sort of additive. Yes, you can think of it as a vector. You can think of it, some of it pointed this way and some of it pointed up. So you are going to have a cancellation in the portions that are pointed at each other, but you are going to have a portion pointed up. And as you get them closer together, that's going to get bigger and bigger and bigger. So they're going to be additive inside. They're in general pointed in the same direction. So you're going to have strong field inside of here as you push them together, because you can see they're sort of pointed, not exactly in the same direction, but as they get closer together, they're going to be more and more, if you can think about the ones coming this way, they're going to be aligned up more and more, and it's going to get very, very strong magnetic field in the center. So the magnetic field, you square it, and then you divide by two numbers. This is a number and this is a number. So basically the energy density is just related to the magnetic field strength squared. The higher the magnetic field, the more energy it stores, right? We can build electronic devices, coils of wire that store lots of energy in magnetic fields that can be released in other situations, right? In circuits, for instance. The best way to think about stored energy is a rubber band. If I pull a rubber band, I'm storing energy in that rubber band. How is it stored? In the electric attraction between the atoms, which are now being stretched apart. It's wanting to pull them back together. So there's energy stored in the electric field between atoms and electrons, and there's energy stored in the magnetic field that exists in space. And where the magnetic field is strongest, then the energy is going to be higher. But the stronger the magnetic field, the more energy is stored. So you have to think about, how does the universe operate? The universe operates by going from high energy to low energy. This marker has potential energy from the gravitational field of Earth. Here it is at a high potential energy. When I let it go, it's going to move down to a lower potential energy because it's closer to the ground. Everything in general wants to travel towards lower energy. If you start asking me questions like, well, why does everything try to go to lower energy? I am sorry, I can't help you, but that is how our universe works. The rules that are in place are that things tend to wind down towards lower energy. When you drop things, they go from high energy to low energy. When you have temperature, a very hot cup of water, it tends to cool off because it's going from high energy, high movement of the atoms, to low energy, low movement of the atoms. When you stretch a rubber band, that's high energy. You let it go, it goes to low energy state. And if you try to push these magnets together, it's going to be trying to make a stronger and stronger magnetic field in the center, which is going to raise the energy of the energy stored there. And the universe never wants to go to a higher energy state. That goes against the laws of nature. So when you put two magnets together, because the magnetic field is trying to get stronger in the middle, storing more energy, it's going to resist that. In other words, I have to put work in to store the energy there. Let me say that again. I have to put work in from my chemical reactions in my muscles. I have to do work on the magnets to store the energy that is now higher between the magnets. Because when I put them together and force them together and hold them there, then I've now stored energy in the field. Where did the energy come from? It came from my muscles. Where did that energy come from? It came from the food I ate. Where did that energy come from? The chemical bonds of the food I had. So the energy came from somewhere, the food, and into the magnetic field. When I let it go, they tend to push apart because the energy is then released, and the universe tries to move towards lower energy states. Just like the marker goes from high to low, the child on the slide goes from high to low, the rubber band goes from high to low, the cup of coffee goes from hot to cold. High energy to low energy. That's why they repel, because as you push them together, you're trying to make the field stronger there, which means more energy there. It's like trying to go uphill on a slide. You're going to have to fight and do energy and work on yourself to climb a flight of stairs. That's just the way the universe works. Now, let us talk about the opposite situation. Let's talk about the situation where now I have two bar magnets. And instead of this, I put this as the North Pole here, and I put this as the South Pole here. You already know what's going to happen. Opposites attract, so they're going to come together. Let's see if we can understand it. The magnetic field exits and enters here, exits and enters here. It comes out here and enters here. It comes out here and it enters here. It goes out of the North Pole, always into the South Pole. So out of the North Pole, always into the South Pole. And then it goes out of the North Pole here, out of the North Pole here, and this direction, and into the South Pole here, into the South Pole here. Now I'm going to erase this one because I think this makes it confusing. But you can see the arrow. Actually, let me erase this one as well. I think it's going to be a little clearer if I put, like this, like that. So like this. Notice the direction of the arrows. When I bring these things closer together, notice that this one is going up, but this one at the same location is going down. They're fighting each other. And as I bring them closer and closer together, I messed up my drawing, I'm sorry about that. As I bring them closer and closer together, what is going to happen? This magnetic field is going to tend to cancel with that one and make the magnetic field strength lower. This one is going to be going opposite direction of this one, and it's going to tend to make the magnetic field strength lower in the center here. So as I bring these guys together, I'm going to write down weaker. As I bring them closer together, the field gets weaker in strength. But weaker in strength means weaker in energy storage. And remember, the universe likes to go towards lower and lower energy storage. So two magnets attracting can be explained because when we bring those two poles of the magnet together, we are canceling the magnetic field, making the magnetic field lower between them, which is a lower energy state. Lower energy, it's like releasing energy from the rubber band. The same way the rubber band comes together, the magnets come together, because as soon as that energy starts to get lowered, it is just going to fly together to make the energy lower. Forces in nature generally always push things in the direction of lower energy. Gravity pushes you down the slide to lower energy. The electric forces pull us to lower energy from the rubber band, and the magnets pull each other together or push each other together into a lower energy state together where the field is weaker. You feel a repulsive force because as we try to do this, the field is stronger and we're raising the energy here, and so it wants to resist that. The universe likes to go from high energy to low energy. When you push two magnets together with the same pole, either both north or both south, the same exact thing will happen if you take this. If you can imagine the south pole over here, they're both going to be pointed in the same direction, and the two south poles are going to make a strong field, and it resists that. But if you flip it around, they're going to attract to make the field and the energy stored lower. Now, if you ask another question, well, why does the energy of the universe like to get lower? Well, I don't know, and nobody knows, all right? Or you might say, back to the electron spinning. You might say, okay, that's a neat theory about the electron spinning and how it explains magnetism, but why do electrons spin? I don't know, okay? And also, is it a ball? No, we know it's not a ball. Quantum mechanics is a wave theory. We know electrons are waves, but they have some kind of angular momentum, and nobody has a really good picture to describe how a wavy thing has an angular momentum, which we usually associate with spinning objects in the macroscopic level. Ultimately, one of my favorite people that I've ever studied is a famous scientist named Richard Feynman. Probably knew more about quantum mechanics than most people will ever learn, right? Way more than me. And somebody asked him, hey, explain to me why magnets work. And he thought about it and he gave about a 20-minute answer and ultimately concluded, I can't explain it to you because once you continue asking questions, you get down to the point beyond which anyone has any answers to anything. So all we do in science is we have models of nature, right? Do magnetic field lines exist? Not sure. They're a great calculational tool to calculate how things will behave though. Do electrons really spin? Not sure, probably not, but it's a great calculational tool. It's a good model of how the universe works. Maybe everything is string theory. Maybe everything is waving strings. Maybe angular momentum is something totally different than I can conceive of. But that doesn't make the theories and the ideas worthless. We come up with better and better models to describe the world. This is how I chose to describe how magnetism attracts and repels objects to you. When you bring a magnet next to the paperclip, it aligns the magnetic domains as we drew in the paperclip, and then now we've explained how magnets can attract and repel, and then of course they attract each other. So you're inducing a magnet to form, and then they attract each other. And then of course we talked about this. If that doesn't satisfy you, well, join the club. It doesn't totally satisfy me either, but I think it's the best humanity can do with just making better and better models to describe our world. Well, I really appreciate everybody for hanging out with me today. Magnets really and truly was one of the first things I ever became interested in science. Still one of the most fascinating things that I've ever observed. I think it's fun playing around with them. And I wanted to do something a little different. I think I'll eventually film these with different lighting and a slightly different setup. I think there's a million ways to go, but I hope you agree that I think this is an interesting way to look at the situation and to kind of visualize that three-dimensional field that surrounds a magnet and how it can influence iron particles, which are magnetizable or magnetic materials in the space around a magnet. Please do drop me a line. I'd really like to know, what do you think? Do you want more detail, less detail? What topics do you want? Please drop me a line. I read every comment, and I'll see you in the next one.
Learn anything at mathandscience.com.